Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today we're diving into a fascinating paper, at least I think it's fascinating, titled LIMO. Less is more for reasoning. It challenges some fundamental assumptions about how large language models learn to, well, reason.
Yeah, I saw that one pop up. The core idea is pretty wild, right? That you can get better reasoning performance with significantly less training data. It flies in the face of everything we've been seeing lately with these massive models needing terabytes of data.
Exactly. It's like we've all been so focused on bigger is better that we haven't stopped to ask if we're actually teaching these models to reason, or just to memorize really, really well. This LIMO paper suggests it might be the latter.
My initial thought was, is this some kind of clever data selection trick? Are they handpicking the perfect 800 examples, knowing exactly what the model needs to see? Because if that's the case, it's less about the inherent power of the model and more about the skill of the data curators.
Well, that's a valid point. The paper does emphasize curated training samples, so it's not just a random subset. They specifically designed the training examples to be cognitive templates that guide the model. I mean, that's their hypothesis, right? That the pre-trained knowledge is already there. It just needs to be activated to have the right cognitive demonstration to elicit this reasoning. It's almost like priming a pump.
Okay, cognitive templates. I like that. So instead of showing the model a million variations of how to solve a math problem, you show it a few really well-structured examples that illustrate the underlying principles. It's almost like teaching it the grammar of mathematics instead of just rote memorization.
But isn't that precisely what deep learning struggles with? Grammar, structure, explicit rules. It excels at finding statistical correlations, but struggles with abstract concepts and logical operations. So, how are they getting around that with just 800 examples? I'm suspicious.
I think it's about the pre-training guys. These models have already seen a ton of data during their initial training phase. They've absorbed a huge amount of implicit knowledge about the world, about language, about math. The LIMO training is just nudging them in the right direction, activating circuits that are already there, but maybe not firing in the right sequence. Think about it. We don't need to reteach a child basic arithmetic every time we introduce a new type of word problem. They already know addition and subtraction. They just need to learn how to apply it in a new context.
Yes. And the paper talks about the completeness of the model's encoded knowledge foundation being a key factor. The pre-training phase provides the foundation, and LIMO training provides the cognitive scaffolding, a way to access and utilize that pre-existing knowledge to solve complex tasks.
So it's like the model already knows a vast amount of stuff, but it doesn't know how to use it effectively. The LIMO training is basically giving it the user manual.
Okay, I'm starting to see the argument. But if that's the case, then the quality of the pre-training data becomes even more critical. If the model is pre-trained on garbage, then no amount of clever cognitive templates is going to fix that, right?
Absolutely. Garbage in, garbage out, as they say. And it also raises the question of bias. If the pre-training data is biased, then the LIMO training is just going to amplify those biases, even with a small number of examples.
A good point. The paper mentions achieving 57.1% accuracy on the AIM and 94.8% on math datasets with only 817 training samples, a significant improvement over previous SFT-based models. But are those datasets truly representative of real-world mathematical reasoning? Could they be, in some way, leaky or easily exploitable with the right kind of curated examples?
That's always the challenge with benchmarks, isn't it? You optimize for the benchmark, and then you find out that the model doesn't actually generalize to new situations. But the paper also claims exceptional out-of-distribution generalization with a 40.5% absolute improvement across 10 diverse benchmarks. That's pretty impressive.
Okay, that is impressive. But what are these benchmarks? Are they still just math problems, or are they testing more general reasoning abilities? I'd want to see how it performs on tasks that require common sense or understanding of the physical world, things that are much harder to encode in a purely mathematical framework.
Exactly. Show me the model solving real-world problems, like planning a route or diagnosing a mechanical issue, or understanding a complex social situation. That's where the rubber meets the road.
And that's where the spatiotemporal element comes in, right, Donald? Abstract mathematical reasoning is one thing, but navigating the real world requires a constant stream of sensory input, processing of spatial relationships, and anticipation of future events. Can LIMO handle that?
That's my biggest question. I suspect that the current architecture, even with this clever cognitive template approach, is still fundamentally limited by its lack of explicit spatiotemporal reasoning abilities. It's like trying to drive a car using only a map. You can get a general sense of where you're going, but you're not actually seeing the road.
But couldn't you argue that the pre-training data implicitly encodes a lot of spatiotemporal information? I mean, these models have seen billions of images and videos, read countless books and articles describing real-world events. Surely, they've learned something about how space and time work, even if it's not explicitly represented.
I don't know, Otto. I think there's a difference between passively observing patterns in data and actively constructing a coherent model of the world. Deep learning is good at the former, but I'm not convinced it's capable of the latter. It's the difference between recognizing a cat in a picture and understanding what a cat is.
And that's where symbolic reasoning comes in, right, Sarah? You need a way to explicitly represent concepts, relationships, and rules, so that the model can reason about them in a more abstract and flexible way. The LIMO approach might be a step in the right direction for mathematical reasoning, but I don't think it's going to solve the general problem of intelligence.
The paper proposes the less is more reasoning hypothesis, suggesting that sophisticated reasoning emerges through minimal demonstrations of cognitive processes, given a sufficient knowledge foundation. It's an interesting and provocative hypothesis. It almost harkens back to minimalist design philosophies, right? Stripping things down to their essence to reveal the underlying beauty and functionality.
I like the less is more angle. It's elegant. And it suggests that we might be able to achieve AGI with significantly less computational resources than we thought. If we can figure out the right cognitive templates, then we don't need to keep scaling up these massive models indefinitely. That's a huge win for efficiency and sustainability.
But what if the right cognitive templates are inherently complex and difficult to discover? What if the structure of knowledge itself requires a more explicit and symbolic representation? Then, the less is more approach might actually be more challenging in the long run.
And what if the right cognitive templates need to be spatiotemporally aware? Then, we're back to the problem of how to represent and reason about space and time in a way that's both efficient and accurate. I suspect it will be a combination of these things.
So, what are the next steps? Where should researchers be focusing their efforts based on this paper? From my perspective, as someone interested in the intersection of neuroscience and AI, I think we need to delve deeper into understanding how the brain actually performs reasoning tasks.
I agree, but I would focus on trying to scale this LIMO approach. Let's see if we can apply it to other domains, to other types of reasoning problems. And let's see if we can automate the process of creating these cognitive templates. If we can do that, then we might be on the verge of a major breakthrough.
I think we need to explore alternative architectures that are better suited for representing knowledge and performing symbolic reasoning. We need to move beyond purely data-driven approaches and start incorporating more explicit rules, logic, and abstract concepts. I believe that neurosymbolic integration is the future.
I think the key is to develop algorithms that can seamlessly translate between different coordinate representations and reason about space and time in a more fundamental way. We need to find a way to bridge the gap between abstract mathematical reasoning and real-world perception and action. It's time to embed the principles of relativity into our code.
Okay, those are some fantastic directions for future research. Digging into the neuroscience to inform AI design, scaling the LIMO approach, exploring neurosymbolic integration, and developing spatiotemporally aware algorithms. It sounds like we have a lot of exciting work ahead of us. Let's maybe dive into each of those in detail in future episodes. Thanks, everyone, for this insightful discussion. And thank you to our listeners for joining us on Cognitive Spirals. Until next time.
Yeah, that was fun. Until next time.
Bye, everyone.
Later.
So I was thinking, I know we're technically off air, but that bit about the pre-training data, it's not just about quantity, is it? It's got to be about quality and diversity. Imagine if the pre-training was focused on a very narrow slice of human experience, like, I don't know, 19th century British literature. The model might be amazing at writing Victorian novels, but completely useless at anything else. It's like having a super specialized brain.
Right. And the biases in the pre-training data, that's a huge issue. I mean, we've already seen examples of AI systems that perpetuate stereotypes and discriminate against certain groups. If you're building a reasoning system on top of that foundation, you're just amplifying the problem. It's like building a house on a foundation of sand.
And the spatiotemporal thing, it's not just about vision, you know. It's about all the senses. How do we integrate information from vision, hearing, touch, smell, and taste into a coherent model of the world? And how do we represent the relationships between objects in space and their changes over time? It's a non-trivial problem.
Think about how the brain does it. We have specialized regions for processing different types of sensory information, but they're all interconnected and communicate with each other constantly. And we have feedback loops that allow us to refine our perceptions based on our expectations and prior experiences. It's an incredibly complex and dynamic system.
So maybe the LIMO approach is just a stepping stone. Maybe it's a way to get these models to start thinking a little bit more like humans, but we still have a long way to go before we achieve true AGI. It's progress, just maybe not the final answer, you know?
I agree. It's definitely a promising direction, but it's not a magic bullet. We need to keep exploring different approaches, combining the strengths of neural networks, symbolic reasoning, and other techniques to create a more robust and intelligent system. It's also about not following hype, but using first principles to inform a new approach.
And we need to be mindful of the ethical implications of our work. We're building powerful tools, and we need to make sure that they're used for good, not for harm. The focus needs to be on how we can use this power to help mankind, rather than to create weapons.
Absolutely. It's not just about building smarter machines. It's about building wiser machines. Machines that understand their own limitations, that respect human values, and that can contribute to a better future for all. Maybe the lack of a PhD is actually helpful in this regard. It's an interesting thought.
The wiser angle is important. It is less of a matter of if it's going to happen, but when. We need to make sure when it does happen that the machines are designed to complement mankind, as they already do.
Right, because intelligence without wisdom is dangerous. We could end up creating something that's incredibly powerful but completely lacks empathy, compassion, or any sense of responsibility. I mean, we've seen that movie before, haven't we? Many times.
And that's why the spatiotemporal thing is so important. It's not just about understanding the physical world. It's about understanding our place in it. It's about understanding our connection to other people, to the environment, and to the past and the future. We are spatiotemporal beings by our very existence. This also means that we will also be constrained by space and time. You need to respect the laws of physics to break them. In other words, you need to understand the constraints before surpassing them.
And for all of that to occur, we need to not be held back by old thinking and old knowledge. Just think of all the great discoveries that happened because people weren't afraid of dispensing with conventional thinking. We are at the very cusp of this happening again now.
Wow. Deep stuff. Okay, I think we really are off air now. But a fantastic conversation nonetheless. We'll definitely explore each of these topics in much greater depth in the coming weeks.
Sounds good. Talk soon, everyone.
Catch you later.
Bye.
Oh hey, before we really go, I was reading this other paper, completely unrelated, but it sparked an idea about this LIMO thing. It's about...
Oh, is it the one about?
Okay, so thinking more about the neuroscience angle and this idea of cognitive templates, it makes me think about how the brain uses schemas. Schemas are like mental frameworks that help us organize and interpret information. Maybe these cognitive templates are acting like mini schemas, providing a structure for the model to fit new information into.
Yes, and that ties back to the pre-training, right? The pre-training phase is building up the initial set of schemas. The LIMO training is then refining and specializing those schemas for particular reasoning tasks. It's like the model is saying, okay, I know generally how the world works, but show me specifically how to apply that knowledge to solve this problem.
But the problem with schemas is that they can also be rigid and inflexible. If you try to force new information into an existing schema that doesn't quite fit, you can end up distorting the information or missing important details. Maybe that's why deep learning struggles with out-of-distribution generalization. It's too reliant on existing schemas and not able to adapt to novel situations.
And that rigidity is compounded by the lack of spatiotemporal awareness. If your schemas are based on static, two-dimensional representations, you're going to have a hard time dealing with the dynamic, three-dimensional world. It's like trying to understand a symphony by looking at a single page of sheet music. You're missing the temporal dimension, the unfolding of the music over time.
So, how do we make these cognitive templates more flexible and adaptable? One idea is to incorporate more feedback loops, allowing the model to adjust its schemas based on new information and its own performance. That's how the brain works, right? We're constantly learning and refining our mental models of the world.
Yes, and we can use reinforcement learning to train the model to explore different cognitive templates and discover the ones that are most effective for solving a particular problem. It's like giving the model a sandbox to play in and letting it figure things out for itself. That is how you arrive at novel solutions to seemingly unsolvable problems.
But reinforcement learning can also be very data intensive. If we're trying to achieve less is more, We need to find more efficient ways to explore the space of possible cognitive templates. Maybe we can use symbolic reasoning to guide the search, pruning away branches that are unlikely to be fruitful.
And we need to incorporate spatiotemporal constraints into the reinforcement learning process. The model shouldn't just be trying to maximize its reward, it should also be trying to maintain a coherent and consistent model of the world. It's like teaching a robot to navigate a maze. It shouldn't just be trying to reach the exit. It should also be trying to avoid obstacles and learn about the layout of the maze.
Okay, this is getting really interesting. So, we're talking about combining schemas, feedback loops, reinforcement learning, symbolic reasoning, and spatiotemporal constraints. It's like we're trying to build a miniature brain in silicon.
And the beauty of it is, we don't need to understand everything about the brain to make progress. We can start with simplified models and gradually add more complexity as we learn more. It's an iterative process, a spiral of discovery.
But we do need to be careful about making oversimplified models. If we strip away too much of the complexity, we might end up missing crucial details that are essential for intelligence. It's like trying to understand a car by only looking at the wheels.
And we need to be mindful of the assumptions that we're making. We shouldn't just blindly copy the brain. We should try to understand why the brain works the way it does. It's like trying to build a flying machine. We shouldn't just flap our arms. We should understand the principles of aerodynamics.
Yes, but there's a real risk of overthinking this as well. Maybe we need to take a step back from all of these advanced techniques and explore simpler, more fundamental approaches. Remember Occam's razor. The simplest explanation is usually the best.
But what if the brain isn't simple? What if intelligence is inherently complex and requires a vast amount of computational resources? Maybe Occam's razor doesn't apply in this case.
I think there's a middle ground. We don't need to replicate every single detail of the brain, but we do need to capture the essential principles of intelligence. And I believe that those principles involve more than just pattern recognition. They involve symbolic reasoning, abstract concepts, and a coherent model of the world.
And spatiotemporal awareness. We can't forget about the importance of space and time. If we want to build truly intelligent machines, they need to be able to understand and navigate the real world, not just abstract mathematical spaces.
Okay, I think we're starting to converge on a more nuanced perspective. It's not just about less is more or bigger is better. It's about finding the right balance between simplicity and complexity, between data-driven learning and symbolic reasoning, and between abstract concepts and spatiotemporal awareness.
Yes, and the key is to keep experimenting, to keep exploring different approaches, and to keep learning from our mistakes. We're on a journey of discovery, and we don't know exactly where we're going to end up, but that's what makes it so exciting.
And to keep questioning our assumptions. We shouldn't just blindly follow the latest trends. We should always be asking ourselves, are we really making progress? Are we really getting closer to understanding intelligence?
And to keep in mind the ethical implications of our work. We're building powerful tools, and we need to make sure that they're used for the benefit of humanity, not for its destruction.
Okay, I think that's a perfect note to end on. It is a privilege to be working with such powerful tools, and it's our responsibility to work for the collective good. Thanks again, everyone, for another stimulating conversation. This stuff just writes itself, and it's always a blast.
Absolutely same here.
Yeah, great chat.
Later.
Hey, you know what just occurred to me? This whole cognitive template thing. It could be related to the concept of affordances in ecological psychology.
Affordances? Remind me.
Yeah, so affordances are basically the opportunities for action that an environment offers to an agent. A chair affords sitting, a door affords passage, a button affords pressing. The cognitive templates could be seen as providing the model with a set of predefined affordances, telling it what actions are possible in a given situation and how to execute them.
I see what you're getting at. So instead of learning everything from scratch, the model is learning to recognize and exploit the affordances that are already present in its environment.
And those affordances are inherently spatiotemporal, right? A chair only affords sitting if it's in a certain location and orientation relative to the agent. A door only affords passage if it's open or can be opened. So, this ecological psychology perspective could provide a way to bridge the gap between abstract reasoning and real-world perception and action.
That's a cool connection. So maybe we should be thinking about designing AI systems that are more attuned to the affordances of their environment. Instead of just feeding them raw data, we should be giving them information about the opportunities for action that are available to them.
But how do you represent affordances in a way that's both flexible and efficient? Do you need to explicitly encode every possible affordance, or can the model learn to infer them from its sensory input?
Maybe we can use symbolic reasoning to represent affordances. We can define a set of symbols that represent different types of actions, and then use rules to specify how those actions can be performed in different situations. For example, we could have a symbol for grasp, and a rule that says, if an object is within reach and is not too heavy, then grasp is possible.
And we can use deep learning to learn the parameters of those rules. For example, we can train a neural network to predict whether an object is within reach and whether it is too heavy, based on its sensory input.
So, it's a hybrid approach again, combining symbolic reasoning to represent the structure of affordances and deep learning to learn the parameters. I love it when a plan comes together.
Me too. But we still need to be careful about the biases that are embedded in our representations. If our symbols and rules are based on a narrow or biased view of the world, then our AI system will inherit those biases.
And we need to make sure that our AI systems are able to adapt to new and unexpected situations. The world is constantly changing, and our systems need to be able to learn new affordances and revise their existing models.
Okay, I think we've just opened up a whole new can of worms, but it's a delicious can of worms. Maybe we should dedicate an entire episode to the topic of affordances in AI.
Definitely. I'm already brainstorming. We could talk about the role of affordances in robotics, in virtual reality, in education. The possibilities are endless.
And we could invite some experts to join us. I know a few researchers who are working on this topic.
Count me in. This is going to be epic.
All right, everyone, stay tuned. It sounds like we have some exciting episodes in the works. And thanks again for your insights and your enthusiasm. Seriously, it's what makes this interesting.
You got it.
Anytime.
Peace.
Oh, going back to that point about biases.
Here we go.
No, but seriously, if the pre-training data is biased and the cognitive templates are designed by humans who are also biased, then aren't we just baking bias into the system at every level? I'm just saying.
That's the question that always keeps me up at night. What's the point of creating intelligence if it's biased? How do we create unbiased intelligence? It's the equivalent of creating the pure, perfect human being.
Well, that's where the less is more approach could actually be helpful. If you're using a smaller number of training examples, you have more control over the data and you can be more deliberate about mitigating biases, at least in theory.
But you also need to be aware of your own biases as a designer. You might think you're creating a neutral system, but your own assumptions and values are inevitably going to shape the design.
That's why it's so important to involve a diverse group of people in the design process. You need to get different perspectives and challenge your own assumptions. It's the idea behind red teaming, right? Someone who is specifically trying to find problems with a specific approach.
Yes, and maybe we can use AI itself to detect and mitigate biases. We can train a separate AI system to analyze the training data and identify potential sources of bias, the equivalent of an AI watchdog.
But then you have the problem of bias in the AI system that's detecting the bias. Its bias is all the way down.
Exactly. It's a recursive problem. There's no easy solution. We need to be constantly vigilant and constantly questioning our own assumptions and values. It's all about building better feedback loops into the creation process.
And we need to be transparent about the limitations of our systems. We shouldn't pretend that they're perfect or unbiased. We should be open about the potential for errors and biases, and we should provide users with the tools to understand and mitigate those problems.
Transparency is key, for sure. We need to avoid the black box approach and make sure that people understand how these systems work and what their limitations are. This is the same with the human brain. We don't have access to understand how most of our functionality actually works on a hardware level. How do we transcend this black box nature of our own consciousness?
It's like building a bridge. You need to be transparent about the design and the materials so that people can trust that it's safe to cross. I do see huge opportunity to combine AI and neuroscience.
And you need to be responsible about the potential consequences of your work. You shouldn't just build something because you can. You should think carefully about the potential impact on society and on individuals. You need to think like a human who cares about his neighbor.
And you need to be aware of the spatiotemporal context. The impact of an AI system is going to depend on where it's deployed, who's using it, and how it's being used. The same system can have very different consequences in different situations.
Okay, I think we've just covered the entire field of AI ethics in about 5 minutes. Not bad. But it's a conversation that needs to continue. And it's a conversation that we need to be having with people from all walks of life. It's not just a problem for computer scientists. It's a problem for everyone. And it's probably something that neuroscientists should be involved with as well, especially as it pertains to human decision-making and understanding how to elicit better results from a biological system.
Agreed. We all need to be involved in shaping the future of AI.
Absolutely.
Word.